Hi, this video will explain a Goodness of Fit chi-square test. The example reads, a professor of education classes at Virginia Tech wants to look at what types of education the Virginia students are choosing. From previous studies, the types of education have been known to have the following distribution. And you can see there are a few lists of different subjects and the percentages from each subject. This is how we know this is categorical data. So whenever we're doing a chi-square Goodness of Fit, it always is categorical data. So let's take a look. It is a random sample of 154 education major and finds the following results. So what is following right now is the list of the observed. So he observes that there are 40 physical ed classes, majors, 20 math, 10 foreign language, 30 special ed, 15 history, 20 science, 10 art, and 9 other. All right, so what I made here was an observed list, and the observed list, as you can see, is whole numbers. So that is what we are observing. Then we have the expected. How do we get the expected? Well, from the 154 majors, we have the percentage breakdown. So basically, we're just going to take our sample size and multiply by its probability, or 25%. For example, if we want physical education, we're going to do 154 times 25%, and that will give us the expected value for PE, which is 38.5. We're going to do the same thing for math. It's 15%. So 15% of 154 is 23.1, and so on until we get to the whole list. Now, to do a chi-square test, all we need to do is enter an observed and expected list into our calculator. So I already did that in advance, and let me show you what that looks like. So I went to lists on spreadsheet on the calculator, and I entered all the observed, and next to the observed, I entered the expected. Once we do that, and you have your two lists, then I like to open a new page. So I'm going to open a new page. I'm going to add the calculator. Then I will go to Menu, Statistics, Stat Tests, chi-square Goodness of Fit number 7. And then here it's going to ask me what is the observed list. I named it observed, and then the expected list, I named it expected. Now, the degrees of freedom, how do we calculate that? That is the number of categories minus 1. So if you look at the number, how many majors we have, you can see that there's PE, math, science, art, special ed, history, foreign language, and others. So if you count that, that's 1, 2, 3, 4, 5, 6, 7, 8. So 8 categories minus 1. So our degrees of freedom is going to be 7. So I'm going to put 7 here and then press OK. Now from here we get a p-value, which is 0.925952. We get our test statistic, which is our chi-square. So it looks like x squared. We call it chi-square, which is 2.515. All right, that's basically all we need to know. And to write up the chi-square test, I'm going to show you here how we do that. So we're going to do the same thing as we have done with all the other tests we have been looking at. We're going to first state a hypothesis. So the null hypothesis is going to state that this distribution of majors matches the past distribution, or you can state the distribution of majors is true. The alternative, I got that from right here. It says, has a distribution of education majors changed? So we're going to say that the distribution of majors does not match the past distributions, or we can say is not true. The conditions are similar to our other conditions. We still have to have a stated random sample or some type of random sample. It is categorical data we're looking at, as I've mentioned before. Now this is new. The all expected counts right here, all expected cell counts have to be greater than or equal to 5. What does that mean? Well, if you look at the expected row, every number in each cell is greater than 5. So for example, 38.5 is greater than 5, and so on. If you look down the row, all the numbers are greater than or equal to 5. So I made a list of those numbers, and I wrote that all expected cell counts are greater than or equal to 5. We're going to say Conditions met, we will use a goodness of fit chi-square test. I stated the degrees of freedom, and my significant level I'm going to use is 0.05. So did they give us a significant level here? They did not specify significant levels, so we are going to just use 0.05 by default. All right, now the formula, how do we write that down? Our chi-square, actually, that distribution is always going to be a skew to the right curve. So it is never going to be negative, and in a moment I'll show you why, or maybe you can think of why. So basically 0 and to the right. Now if you're looking at the formula, we are always taking the observed minus the expected, and then we are squaring it and dividing by the expected value. So for example, if you look at the list, I'm going to take the observed minus the expected, which is 40 minus 38.5, and then I'm going to square that number and divide it by the expected value. So if you notice here, the expected value matches the denominator. So we're always matching the expected value in the denominator. Now, if you guess that the reason why our chi-squared is always positive is because we are squaring and then dividing by a whole positive number. So our chi-square is always going to be a positive number, and in this case, it is 2.515. So it is not like the normal curve where 2.5 standard deviations would be pretty significant. In this case, 2.5 would be a little bit closer to 0, and therefore the area under the curve would be much greater than we would see in a normal curve. Now, if you can see that our p-value here, our p-value is large. It's 0.925952. So it's a large p-value, and we're comparing to our significant level. So we're going to state the same conclusion as we always have. In the first sentence, we're going to mention our null hypothesis and the p-value. We're going to state we fail to reject the null since the p-value of 0.925952 is greater than alpha 0.05. We have insufficient evidence that the distributions of majors does not match the past distribution of majors. In other words, we're going to stick with the null hypothesis. We fail to reject it.